I'm going to talk to you about the multi-geometric neural network, but before we dive specifically into that, I want to talk to you about the precursor, how I got to it, and kind of my thoughts for this experiment up front. It starts with this research paper, NGPT, Normalized Transformer with Representation Learning on the Hypersphere. This was put out by NVIDIA, and it was put out in October 1st of 2024. This paper was sent to me by someone within my network. They just sent it to me. I understand, and once I dissected this paper, I understood exactly why they sent it to me, and I can't appreciate them enough. So this particular paper is interesting. This particular paper, so the hypersphere, with regards towards this instance, deals with the shape of a neural network within Euclidean space. And then so essentially they use Euclidean space to create a sphere, and then they fix the dimensions of the sphere. Let me see if there's so this is their mathematical equation within it. And then they do some normalization of the transformers via this sphere, right? But it's all essentially based off of this sphere and geometric logic. And so this hypersphere is essentially what they're doing, right? I'm trying to find a good diagram within essentially like within their method. I don't think they have it within here. But so essentially what they're doing is so it's a Euclidean geometric sphere, and then they normalize it, right? So it's you have normalized distances between the points on the sphere. So like 1, 1, 1, 1, 1, and they're all equaled out, as opposed to, let's say, like a hyperbolic space, which you can't make these same distance equations, right? And then so to me, what catches my eye, and I'll go over here, what makes this most interesting to me with regards towards this paper overall, is the fact that they're utilizing Euclidean space within this, right? And they're utilizing Euclidean space very specifically. Like they could have created a Poincare sphere in hyperbolic space, but they didn't. They created a Euclidean sphere. And they did it very specifically because they wanted to fix the distances, right? They knew with a Euclidean sphere, they could make it so it has those fixed 1, 1, 1s across, like all across, as opposed to with a hyperbolic sphere, which they couldn't do. And so a lot of my research, a lot of what I dive into, a lot of like kind of where I'm going is more and more into like hyperbolic space, because it's my hypothesis is that the universe is hyperbolic, that the physical universe is hyperbolic. There's a curve in space, and that's what creates everything, right? But within that, so what is real and what is not real doesn't necessarily matter when we're training AI models overall, right? And that's kind of an important concept within this. And like, I think it's important to keep that distinction in mind when you're going within this, right? So whether or not Euclidean space or hyperbolic space is the real digital space, it doesn't matter. They both serve different purposes. And then so you have Euclidean, hyperbolic, and fractal spaces within this instance, and which one of these is more real than the other, I don't know. Taking out the philosophical discussions out of them, they operate differently, and they have different mechanics that govern them. And then so taking that just one step further, like what no one has done to this point is taken these different mechanics from these different spaces and literally make each one of these mechanics a different layer of a neural network. Like a Euclidean space has a different physics than hyperbolic space, which has a different physics than spherical space, which has a different physics than fractal space. And then so if you combine all these, you have an individual layer of Euclidean space and an individual layer of hyperbolic space and an individual layer of spherical space. You have 3 different layers, right? And so that's what I do within this. So this notebook implements a neural network architecture that operates across multiple geometric spaces, allowing layers to process and transition between, in this instance, Euclidean, hyperbolic, spherical, and fractal representations. Unlike traditional deep learning models that assume a single underlying space, usually Euclidean, this architecture enables dynamic, multi-manifold learning where each layer operates within a different geometric structure. Key features. Layer-specific geometry. Each layer can be defined in Euclidean, hyperbolic, spherical, or fractal spaces. Geometric transition. The network adapts representations across layers using inter-manifold transformations. For example, Euclidean to hyperbolic, hyperbolic to spherical. Fractal representation learning. A Cantor set-inspired fractal layer enforces self-similarity, potentially improving hierarchical learning. I had to build out the fractal layer a lot. It was more built out and harder to do than any of the other layers. Geometrically constrained backpropagation, gradient updates, respect the constraints of each geometric space, improving optimization stability. I'll get to you. So I built out a full neural network, backpropagation, the whole 9 yards, right? So why this matters. Most neural networks assume a single fixed geometric space, real-world structures, for example, like physics, complex data distributions. They often require different geometries at different scales. So this model maps the real world better. That's kind of the goal, right? I figure you give it data in different shapes and in different compression mechanisms, and that's what it's going to do, right? And then so essentially, that's what I do here. So I create essentially, first of all, the calculations to calculate the different distances in the different spaces, right? So Euclidean, hyperbolic, spherical, and then Poincare disk. And then I need to project these images. So I project these images to the different spaces. So spherical, hyperbolic, and Euclidean. Fractal is its own space within this, right? So here we have the helper fractal function. And then with fractal space, how I'm creating the fractal space very specifically within this instance, you might want to know the method. So I project a 2D point towards a simplified Cantor set-like structure. And we're adapting the Cantor set concept to 2D for visualization, creating a grid-like fractal pattern. So I'm using like fractal grids, right? Like it's like a fractal graph is essentially like what I am making the model. Like this is the fractal layer of the model. Like fractal layers can be chaotic. It's a lot of different ways to handle this. So like a fractal graph is like how I decided to build this into the model. And I thought it would be important to build a fractal layer into the model. I'll show you here in a second why, right? So we go into the layer classes, and then I need to put these all together into an actual neural network. So in this first instance, I just have the feed forward mechanism, no backpropagation up first, right? I just want to make sure it works. So can I actually like implement ReLU within this? Like will everything actually function properly if I do this, right? So I just have the forward pass. I do the forward pass through the whole entire network, and then what I want to do is I want to visualize with this, like what is this going to look like? And then so that's essentially what I'm doing, right? Is I'm plot out, like give me some input data, and then have it go through the layers and what happens. And then this is very specifically what happens, right? And this has been my assumption for a long time. Like this is what gets me here, right? Because this is like I have assumed that these models are doing this for a while now, right? And then so they take the data and then they compress it, and it's all compression, right? Compress and reshape. Their ideal situation would be to compress this data into like that little tiny circle right there on the right, right? Like the right is the ideal state of this data to the model. The first state is a good measurement pattern for being able to reconstruct that fuller, larger image from the dot. But the model wants the dot. Like that's the data that it wants more than any of these other rows. It wants layer 4. Layer 4 is the best layer to this model. And then so within that, I take it a step further, right? So this next one is okay, I can prove this concept out. This is what it works, this is what it does, this is how it works, and this is all expected, right? And then so now let's test the performance of this model. And then so I do this, I build out the same thing, I build out the same model, a lot of the same architecture. I'm just adding in this instance, I add backpropagation, and then I actually add a training mechanism, and we're training it on, in this instance, the iris dataset. And then so I just, I have backpropagate, and I had to, again, highlight, I think the fractal layer is the hardest part of this. The three other layers were super easy compared to the fractal layer, and then the fractal layer requires its own math in every single part of it. So include, like, when I added the backpropagation, more math just for the fractal layer as well. You go through, and then you combine all of that, and then you get your predictions. We load a model, train it. Oh, and then so I trained it initially for 100 epochs, right? And then so you can see here 96.67% accuracy. This model cooks. This is cooking up and baking in the oven right now. But when I first ran it, it was 100. I ran it for 100 epochs, and then what happened was, like, right around here, like okay, you can see it perfect. So you can see, like, this is like good loss rate. Like it's losing and going down, right? Loss rate is decreasing exactly as expected, and then here a spike, spike, spike. right? And then so there's a chance, like I could have, there's a very good chance that the optimal performance for this model was 10 epochs. I initially ran it for 100, and then I got result it overfit. It was it went down to like 40% because this loss rate went to like 2. It just climbed, like it was just screaming, right? So I could tell, like, okay, I need to consolidate this and make this. I need to decrease my training rate. It's overfitting on this data hard. And then looking at this loss rate as I'm going through this video here, I see the same pattern. The one test I didn't do was right around, I didn't play enough around this range. I think there's a possibility it started overfitting again here, which, going back to this research paper, is exactly what this research paper proves out, right? So the kind of unique takeaway from this research paper that they do, why would you care about this research paper, right? It's they say that utilizing this method, they're able to train the model on 4 to 20 times less data overall. And then that's kind of epiphany for me, right? And kind of important to explain here, because I'm noticing that with my tests. Like what my tests are showing here is I need to train this model less than I think I should. And then I'm used to training models on transformers models, right? And then this is screaming to me cut it back. I've already pared it back 50%. My initial was 100 epochs, and then this data is still screaming to me, pare this back more. And then so that's a big thing within this, right? A lot of people are focused on that. Why do you have to have so many passes of the data set over the model in order for it to learn? It's transformers, bro. You keep saying that. There's problems with the transformers architecture in and of itself. If you get around that, you don't have the same problem. This model is literally overfitting. If you trained this model the same way you trained a transformers model, you'd have an overfit model every single time. And then so cool. I'll leave a link to this collab. If you like this type of content, please like and subscribe. Thank you very much.